Finally, we get to talk about methods of proofs. In the first part, we're going to talk about how to prove implications. I'm going to discuss 3 ways of proving P implies Q. The first method is called the direct method. The principle rather, of this method is to assume the hypothesis and deduce that the conclusion is true. So let's demonstrate this with an example. Prove that if n is odd, let n be a natural number. Prove that if n is odd, then n squared is odd. Okay, so we're going to, as I mentioned, assume that, we'll repeat the assumption of n a natural number, and we're going to assume that the hypothesis, hence we call it assumption, is true. Okay, so what is an odd number? An odd number is a number for which when you divide by 2, there's a remainder of 1, right? In other words, there exists, let me just say, it means that there exists, let's call it k, a natural number such that n is equal to k plus 2k plus 1. Okay, now that we have n is equal to 2k plus 1, we can take the square of this number. So let's square this number. N squared is 2k plus 1 squared. We can expand this to get 4k squared, plus 4k plus 1, right? And our main goal is actually to write, because we want to prove that n squared is also odd, we want to write this one right here as 2 times something plus 1, right? 2 times a natural number plus 1. What we can do is we can factorize 2 out, and we get 2k squared plus 2k plus 1. Okay, so at this point you can say that n squared is an odd number, or if you want to give more details, you can write the following. Set m to be 2k squared plus 2k, which is a natural number, since k is a natural number. Therefore, n squared is equal to 2m plus 1, i.e. n is an odd number. And we are done with the proof. So again, we assume that P is true, and we deduce that Q is true. I have alluded to this method in the implication video, that another way to prove an implication is to prove its contrapositive. So assume Q is false and deduce that P is false. Okay? So we want to, in order to prove P implies Q, we prove not Q implies not P, which we know is equivalent to P implies Q. Okay, let's take a look at this example. Let n be in n. Prove that if n squared is odd, then n is odd. Okay? In the previous example, we start with a number that is odd, and then we show that the square is odd. This is the opposite, right? But as you can see in the previous example, that it's nicer to start with a number and then take a look at the square, right? So it makes sense to rather prove this directly. We prove it's contrapositive, because what is the contrapositive? Let's write it down. Right? We prove it's contrapositive which is what? Let's repeat the assumption again. Here, let n be in n, we prove it's contrapositive. That is, if n is even, if not q, right? Not q, not n is odd, is n is even, then n squared is even. Okay. So now we're going to prove this implication directly. Okay? So assume that n is even, i.e. there exists a natural number k such that n is a multiple of k. That's what it means by n being even, right? Thus, quite similar to the previous one, n squared is 2k squared, which is 4k squared, which is 2 times 2k squared, right? We can also just say here another even number. If you want, you can also, like in the previous proof, set this to be a natural number and so on and so forth, but let's skip that one for now. I think we all got the point. Okay, the third method of proving P implies Q, the first one being direct proof. The indirect proof is to prove it's contrapositive. The third one is proof by contradiction. Proof by contradiction works as follows. You first assume that P is true and assume that Q is false. And then you deduce an obviously false statement and you're done with the proof, okay? But you may be wondering, right? How does this work? Why is this valid? Okay, this works because of the following reasons. So what we're doing here is we're saying that P is true and not Q is true or Q is false. And then we say that this statement is false because we assume this and we deduce an obviously false statement. This is how proof by contradiction works. Okay, so now not P and not Q, so the negation of this guy is of course going to be true, right? But what is this? What is P and not Q? This is not P or Q, right? I'm mixing my symbols here, but you know what I mean. And you know that this guy is logically equivalent to P implies Q. This is one of the exercises in the implication video, right? So this is why this proof by contradiction works, right? Essentially, we're showing that P and not Q is false, meaning that not P and not Q is true, or not P or Q is true, or P implies Q is true. Let's demonstrate with an example. Okay, let's see proof by contradiction in action. Let n be a natural number. Prove that if n squared is even, then n is even. So let's say let n be a natural number, and then we assume that P is true, n squared is even. And then we suppose that the conclusion n is even is false. Suppose that. You can also tell your readers that you're about to use proof by contradiction for the sake of contradiction. And is not even, i.e. odd, okay? So there exists a k in natural number k such that n is 2k plus 1, right? Therefore, if you look at n squared, this is 2k plus 1 squared, which is 4k squared plus 4k plus 1, is equal to 2 times, this is something similar to what we did before, right? 2k squared plus 2k plus 1, which is an odd number. This contradicts our assumption that n squared is even. That's our assumption, right? Therefore, our supposition is false. What is our supposition? We suppose that n is odd, is false, so n is even. Okay. Okay, I'm going to demonstrate proof by contradiction one more time. This is a classic proof when people first learn proof by contradiction. Proof that square root of 2 is irrational. So we're going to suppose that root 2 is rational, which means that there exists two integers. The one of the integers is not 0. And also, the greatest common divisor of P and Q is assumed to be 1, such that root 2 is equal to P over Q. Okay, this part right here, greatest common divisor of P, Q equals 1, it means the following, that I am looking at the fractions of its simplest form. So for instance, 3 over 6, 2 over 4, and half, they are the same number. It's actually half. So we don't want that form, we don't want that form, we always want the simplest form. Okay. Then, let's be consistent with the ink. Then P is root 2 times Q, right? Simple algebra. And so P squared is 2 times Q squared, right? Which means that P squared is even. Okay? Because P squared is even, what's happening here? So P is also even. And there exists an integer m such that P is 2 times m, okay? So P squared is equal to 4m squared, right? And because P squared is also equal to 2q squared, what we have now is that 2q squared is equal to 4m squared, which implies that q squared is 2m squared, right? And so q squared is also even, and q is even, right? But remember that we assume the greatest common divisor of P and Q is equal to 1. So it cannot be the case that both P is even and Q is even, right? So this contradicts the fact that the greatest common divisor of P and Q is 1, and so root 2 is irrational. And we are done. Okay, this last part is a bonus content, so if you want to skip it, feel free to do so. I just want to talk about vacuous proof. In the truth table for the implication P implies Q, remember that when P is false, Q may be true or false, right? That was the third and the fourth line. In order for the implication to be true, right? In such a situation, so when the hypothesis cannot be satisfied, we're going to call the truth of the implication to be vacuous. Okay, so let's see this example. Prove that for any subset of real numbers A, that A contain the empty set. Okay, remember that if we want to prove that A is a subset of B, this is basically proving this implication, right? If X is in A, then X is in B, okay? I should probably use different letters, but anyway, it doesn't matter. So now if we want to show that for any subset of real number A, that the empty set is a subset of A, what do we want to show? We want to show that if X is in the empty set, then X is in A. This is the implication that we want to show, right? But look at this. To say that X is in the empty set is absurd, right? Because empty set has no member. So this hypothesis cannot be satisfied, and therefore the implication is true, regardless of the value of Q, right? Okay, so that's the idea. So I'm going to write the formal proof. Okay, let A be a subset of R, and I'm going to say denote B, let B be the empty set. Okay? Now we're going to take a member B in B, right? Since B is an empty set, or the empty set rather, the statement B in B is false. So the implication B in B implies B in A is true. So let me rather write it down here, is true. Therefore, B, which is the empty set, is a subset of A. And we're done. Okay, that brings me to the end of this video, and I'm gonna continue in the next video with more methods of proofs. Thank you for listening.